Welcome. And let's unpack just a monumental topic today, the human brain. We are diving into a stack of sources that don't just ask how the brain works in a biological sense.
No, it's a much deeper question.
It's asking the fundamental, really challenging question. What kind of computer is the brain? This mission is about finding the deepest, most insightful computational metaphors for the biological machine inside our skulls.
Yeah, and that's a really important way to frame it. Our listener is looking for a thorough but not overwhelming understanding of the brain's computational models. And that means looking far beyond just classical neurobiology.
It's an ambitious deep dive we've got today.
It really is. We are going to explore two radically different maps of intelligence. The first one is machine learning, or ML. That gives us the algorithmic roadmap, the how.
The nuts and bolts.
Exactly. And the second is quantum computing, QC, which offers this, well, it's a speculative but conceptually rich lens for explaining things like consciousness, unity, creativity, what it feels like.
The goal is to bring them together somehow.
Yeah, our ultimate goal is to synthesize these maps into a unified, multi-scale model of human intelligence.
And the hook here, the thing that gets me every time, is the central paradox of the brain. You have this incredibly intricate biological network. We're talking roughly 86 billion neurons, trillions of synapses. I mean, the complexity is astronomical.
It's a universe in there.
And yet, it runs on just 20 watts of power.
20 watts.
It's less than a dim light bulb. This low-power machine achieves consciousness, creativity, adaptation. It makes even the most advanced, power-hungry supercomputers on the planet look primitive.
Completely primitive. Nature figured out energy efficiency and intelligence at the same time.
So how does it pull this off?
Well, it is the pinnacle of biological engineering, and to even begin to understand it, we need those two powerful metaphorical lenses we mentioned. Machine learning gives us the operational language for how the brain learns, how it processes information, predicts outcomes.
Right, what we can call algorithmic intelligence.
Exactly. It focuses on the observable structure, the optimization processes. Then you have quantum computing, which is, and we have to say this up front, highly speculative. Deeply controversial in the neuroscience community.
And for good reason, which we'll get into.
Absolutely. But it offers a vocabulary for features ML just fundamentally struggles to model. Things like the instantaneous unity of subjective experience, nonlinear creativity, sudden intuition.
What you call phenomenological intelligence.
Precisely. And we have to be brave enough to look through both lenses if we want to get anywhere near the whole truth of human cognition.
Okay, let's unpack this classical view first. Our sources argue pretty compellingly that the brain is essentially nature's first deep modular network. And it's still the most efficient one.
Oh, by far.
It's like it invented deep learning before we even had the concept of silicon chips or backpropagation.
That's precisely right. If you look at the fundamental design principles of modern AI, they just mirror biological necessity. I mean, current state-of-the-art architectures, your convolutional neural networks, your RNNs, the giant transformer model.
All big names.
They all process data hierarchically. They build complexity layer upon layer. The brain pioneered this structure millions of years ago, and we are only now in our artificial systems just catching up.
And the clearest, I think, most studied example of this hierarchical structure has to be the visual cortex. The sources call it the original CNN.
It's the perfect example.
So how detailed is this analogy, really, between our own visual system and the way an AI recognizes an image, like a cat on the internet?
It's incredibly detailed. The visual cortex, specifically areas like V1, V2, and V4, processes sensory input in these highly organized stages. It's an exact mirror of the successive filtering layers of a convolutional neural network.
Okay, so break that down. What's happening in layer one?
So, in the first layer of the visual cortex, in V1, the neurons are tuned to detect very, very simple features. Basic edges, lines at specific angles, orientations.
Just the absolute raw components.
For raw components, just like the initial filters in a CNN. Then, as that information moves deeper into subsequent layers, say V2, the brain starts extracting more complex shapes and textures.
So it's integrating those lines.
It's integrating the lines into corners, into curves, into simple patterns. By the time that signal gets to the later, more abstract areas, like the inferior temporal cortex, the system has integrated those basic shapes into full invariant concepts.
Invariant meaning?
Meaning it recognizes the object, a face, a specific car, a whole scene, regardless of the lighting or the angle or how far away it is. This biological cascade of abstraction, that is the foundational principle of all of deep learning.
That makes perfect sense for processing data coming in. But our sources point out a critical biological advantage that a lot of standard AI models, at least initially, didn't have. This idea of recurrent refinement. What does that feedback loop add to the whole picture?
Ah, this is where the biological system just truly shines over those early, simple feed-forward models. The brain isn't just a one-way street, processing information bottom-up from the retina to the cortex.
It's not just a conveyor belt.
Not at all. It actively incorporates these extensive feedback loops or top-down signals from higher-level regions, sending information back to the lower ones. The mind is constantly generating predictions about what it expects to see.
A hypothesis.
A running hypothesis, yes. And then it uses the actual incoming sensory data to update and refine those predictions dynamically in real time.
So if I'm walking through a foggy park, my brain isn't just passively waiting for perfect visual data. It's using context. It's thinking, I'm in a park, that dark shape is probably a tree, and that thought actually influences the lower level processing.
That is exactly what's happening. That top-down signal acts like an active bias. It allows the brain to achieve recognition much, much faster, often on noisy or incomplete data, because it's actively filling in the blanks based on its internal world model.
It's an efficiency mechanism.
A huge one. It prevents the system from having to recalculate every single pixel from scratch every single moment. It's a continuous dynamic loop of prediction and correction. That adds a speed and a context sensitivity that standard deep networks, even the really powerful ones, still struggle to fully emulate without just immense complexity and power draw.
Okay, so that's vision. But let's zoom out and talk about connectivity across the whole brain. We've seen the rise of these giant transformer models in AI, which rely entirely on this thing called the attention mechanism to link data points efficiently, even if they're really far apart in a sentence.
Yes, the attention mechanism is key.
How does the biological brain pull off that same trick? How does it get that efficient long-range communication?
The physical structure of the brain itself gives us the answer. Brain networks aren't connected randomly, like a big bowl of spaghetti. They form what are called scale-free graphs.
Scale-free graphs. What does that mean in practical terms? If we could draw a map of all the brain's connections, what would it look like?
It's a specific type of network topology. It means that the connectivity follows a power law distribution. What you would find is a relatively small number of highly connected nodes. We call them hubs. These ultra-connected neurons or small cortical regions handle massive amounts of traffic. They're the big international airports of the brain. The vast majority of neurons, on the other hand, have only modest local connectivity.
They're the small regional airports.
Exactly. Think of a global transport system. You have key hub airports like Chicago or London connecting distant continents. Most smaller airports only connect to those hubs, or maybe a few nearby towns.
Ah, so the efficiency comes from not having to route every piece of information through every possible connection. You just send it to the nearest hub, and the hub sends it where it needs to go.
Precisely. This structure is so similar to the transformer attention mechanism because it lets the system dynamically reweight connections. It prioritizes information flow based on relevance. If you need to quickly link a memory from the hippocampus to a goal in the prefrontal cortex, the information doesn't have to check every neuron along the way.
It takes the express train.
It uses the scale-free hubs for long-range, efficient, and highly parallel communication. And critically, this structure also ensures fault tolerance. If you lose a local, low-connected neuron, the system barely even notices.
But wait a minute. If the whole structure relies so heavily on these hubs, doesn't that introduce a massive point of catastrophic failure? If one of those major hubs goes down, wouldn't the entire system just crash?
That's an excellent critical question. And yes, that is the inherent risk of any scale-free network. It's a vulnerability. The biological brain manages this risk through a lot of redundancy and plasticity, the ability to rewire.
But the risk is still there. The risk is absolutely there. If a key hub, say the thalamus, which is a massive routing station for sensory information, is damaged, the resulting cognitive disruption is far more profound than the loss of a small local region. It reveals the architectural compromise nature made. It traded absolute localized protection for massive global efficiency and parallelism.
Okay, so the brain is hierarchical. It uses attention-like hubs, and it's fault-tolerant at the local level. But it's also highly modular. Different regions do very specific jobs. Let's dig into those functional analogies, comparing them to specific types of AI models.
The specialization is just astounding. You can think of these specialized brain regions as dedicated functional subnetworks, all inside one massive integrated AI system. Take the hippocampus, for example.
Memory central.
Well, its primary job isn't just storage. It's more about indexing and retrieving context-specific memories. That function is almost perfectly analogous to something called a memory-augmented neural network, or MAN.
Right. A MAN in AI uses an external memory bank to supplement its core processing model. It can look things up. That's it. The hippocampus creates those index tags, the where, the when, the who, that allow you to retrieve a specific experience instantly. It supplements the general knowledge that's stored more diffusely in the neocortex. It acts like a fast, writable memory cache.
Okay, what about the part of the brain we always associate with high-level thought, with planning, with maintaining focus? The prefrontal cortex, the PFC.
The PFC acts like a classic recurrent neural network, or RNN. Its job is to maintain working memory across time. It doesn't just react to the current input, it holds an active state or context that persists as new inputs arrive.
It has a short-term memory.
A very active one.
Yeah.
This allows for planning, for sequential reasoning, for complex decision-making, and that is the exact definition of an RNN's architecture, maintaining a memory of previous states to influence how you process the current one.
And then we have the big one, the vast wrinkled surface of the brain, the neocortex, where most of the heavy lifting happens. How does that operate from a computational standpoint?
Our sources suggest the neocortex operates primarily as a predictive coding architecture. And this is absolutely vital if you want to understand the brain's 20-watt efficiency.
Okay, let's slow down on predictive coding, because this feels really important. Explain exactly how it saves power and guides learning.
So the core idea is that the brain is constantly, at every level, generating a hypothesis or a prediction about the sensory inputs it expects to receive in the very next moment. This is a top-down signal.
It's always guessing what's next.
Always. And here's the clever part. The only information that is then transmitted upwards and outwards from a lower layer is the prediction error.
The surprise.
The surprise. The mismatch between what it expected and what actually happened.
So if I expect the floor to be cold when I step on it, and it is in fact cold, basically no information needs to be transmitted at the temperature.
Very little. The prediction was correct.
But if it's suddenly searing hot, the error signal fires like crazy.
Exactly. The brain only passes forward the surprises. If your internal model of the world is accurate, computation and communication are radically minimized. This is why surprises or novel things command so much of our attention. They represent massive prediction errors that force the system to stop and update its internal model of reality.
So computationally, the neocortex is running a continuous, built-in, self-supervised learning model.
Yes, and it's driven entirely by minimizing its own internal error. It's the most efficient optimization mechanism you can possibly imagine.
That's a beautiful map of the architecture. But if we drill down one layer deeper, our sources remind us that the brain's true computational currency isn't the smooth, continuous activation values we use in classic AI. It's all about spikes.
This is a fundamental difference. The physical language of communication is different. Traditional AI uses continuous floating point numbers to represent activation levels. You can think of it like a dimmer switch.
It can be 0.1, 0.2, 0.73.
Any value in between. But biological neurons communicate via discrete, sudden electrical events called spikes, or action potentials. It's an event-driven dynamic, not a continuous one. It's a light switch, on or off.
Why is that difference so critical for understanding biological efficiency?
Because the spike is an inherently energy-efficient, asynchronous signal. Neurons are mostly silent. They only communicate when there is an event worth communicating. This is the whole logic behind a different class of AI models called spiking neural networks, or SNNs.
SNNs are the brain's true language, then, and they're the goal for neuromorphic engineers.
They are. The promise of neuromorphic hardware, chips like IBM's True North or Intel's Loihi, is to recreate this event-driven architecture. Instead of running clock cycles and massive data transfers constantly, they arrange their processing cores as analogs of axons, dendrites, and somas. They run asynchronously, based only on when spikes arrive.
So they only compute when they need to.
Only when there's new information. If they succeed at scale, they could finally capture the brain's extreme energy efficiency and high parallelism. We're talking about operating perhaps thousands of times more efficiently than classical GPUs. The human brain's entire design relies on this distributed, modular, multimodal system that leverages these discrete, time-sensitive signals.
Okay, so we have the architecture down, and let's get into how this biological machine actually learns. In machine learning, you need two things: a loss function, something to minimize, and a reward system, something to maximize. What are the brain's corresponding organically distributed mechanisms?
Well, as we just touched on, for a huge amount of the learning related to perception, the dominant drive is simply prediction error acting as the loss function. The brain's main job is to maintain the most accurate possible internal model of the world.
So its core optimization drive is self-supervised.
Exactly. Just minimize the sensory prediction errors.
Yeah. And this error minimization has to happen locally, right? The brain doesn't have a giant GPU somewhere calculating a global gradient error for the whole network. So how does biology manage that massive logistical problem?
It's handled through this rich, intricate local system known as the interneuron ecology. We're talking about these specialized inhibitory neurons that implement this local error propagation and signal regulation right there at the microcircuit level.
Can you break down the roles of a few of these biological assistants? They sound crucial.
They are absolutely crucial. This is where the complexity truly is. You have parvalbumin cells, or PD cells. They're fast spiking, and their primary job is stabilizing firing patterns. They keep the activity within a healthy range, preventing runaway excitation.
So they're like the brakes on the system.
A very good analogy. Then you have somatostatin neurons, or SST neurons. These often gate incoming signals to the dendrites. They're essentially filtering and regulating inputs based on where they arrive and how they're timed.
They sound like quality control managers at a factory gate.
That's a great way to think about it. And then finally, you have another type, VIP neurons. That's vasoactive intestinal peptide. And these often modulate the activity of the SST cells themselves.
So they're managing the managers.
In a way, yes. VIP neurons are particularly active based on contextual input, like attention or motivation. If your attention is high, the VIP cells can temporarily reduce the inhibition from the SST cells, making the entire local circuit more sensitive to incoming signals.
That is a highly decentralized, multi-layered error system. It sounds incredibly complex to model computationally. How does a network like that map to something an ML expert would recognize, especially since we know classical backpropagation is biologically implausible?
It maps beautifully to a concept called feedback alignment. Classical backpropagation, as you said, is unrealistic. It requires every layer in a network to receive a precise error gradient calculated from the final output layer, and it requires perfect symmetry in the forward and backward weights.
Which is computationally expensive and biologically messy.
Exactly. Feedback alignment is a whole class of algorithms where approximate, often randomized error signals can propagate locally. The key interneurons we just discussed facilitate this highly distributed, approximate, local error propagation. It allows the system to update its weights without ever needing that global synchronized gradient. It's nature's efficient workaround for gradient descent.
So that handles the error minimization. Now we need the optimization algorithms themselves, the actual biological rule for updating the connection weights.
The foundation, the one taught in every intro neuroscience class, is Hebbian learning.
Neurons that fire together wire together.
That's the one. It's the core biological rule for weight updates. But of course, nature gets highly optimized through something we call synaptic plasticity.
Let's detail the two critical processes of plasticity that the sources really highlight.
Okay, first we have long-term potentiation, or LTP. This is the persistent, long-lasting strengthening of synapses that results from repeated correlated activation. It is the physical mechanism by which memories are encoded and connections are reinforced.
So if you practice a piano piece over and over, LTP is what's physically strengthening the motor pathway connections.
Precisely. And the second key process refines this strengthening based on timing.
Which is where things get really interesting.
This is spike timing dependent plasticity, or STDP. This rule adjusts the weights based on the precise temporal order of the spike firing. If neuron A fires just a millisecond before neuron B, causing it to fire, the connection strengthens significantly.
Suggesting that A caused B.
Exactly. It introduces a causal element. If neuron B fires first, the connection weakens or stays the same. STDP functions as a time-sensitive, biologically grounded version of gradient descent. It doesn't just look at whether two neurons fired, it optimizes connectivity based on their temporal relationship and the implied causality. This leads to much faster, more efficient learning of sequences and dynamics.
Okay, we've covered self-supervised learning for perception and plasticity for refining the connections. But true high-level intelligence requires goal-directed behavior. It needs motivation, maximizing gains, the push to do better.
And that brings us squarely to dopamine, the reinforcement learning signal. Dopamine neurons, particularly those projecting from the ventral tegmental area and the substantia nigra, have a very specific job. They encode the reward prediction error, or RPE.
Okay, explain the RPE mechanism in detail, because this feels like the biological engine of all motivation.
The RPE is simply the difference between the reward you expected to get and the reward you actually received. So let's say you perform an action that historically gives you a reward of, say, 10 units.
Okay.
If this time you get 15 units of reward, the dopamine neurons fire a big burst. That's a positive RPE of +5. It's a signal to the system that says, hey, that was better than expected, reinforce whatever action you just took.
And if you get less?
If you only get 5 units, the dopamine neurons briefly dip below their baseline firing rate. That's a negative RPE of -5. And that signal says, that was worse than expected, weaken the preceding action, or maybe seek some alternatives next time.
This is more than just a loose analogy, isn't it? This is a direct mathematical parallel to AI.
It is mathematically identical to the core mechanism of temporal difference learning, which is used in powerful reinforcement learning, or RL algorithms like Q-learning. The basal ganglia and the limbic system, operating this dopamine loop, are constantly calculating the expected value of various actions and outcomes. They use that RPE signal to shape habits, motivation, and all goal-directed behavior.
So this is how the brain efficiently prioritizes what to do. It literally maintains a running dynamic calculation of which path has the highest expected long-term value.
That's right. So when people talk about motivation or drive or even addiction, they're fundamentally talking about the outputs of a complex biological Q-learning algorithm that's running constantly, trying to maximize future discounted rewards.
Wow. That's a powerful, almost deterministic view of behavior.
Well, it provides the mechanistic blueprint. I mean, if you look at something like addiction, it is often a hijacking of this RPE system. Certain stimuli generate these massive, unearned, positive RPE signals that override the brain's ability to calculate true long-term value. It just shows the incredible power this single computational mechanism has over our choices.
And it's also crucial to remember that this whole training process is continuous. It's happening even when we're seemingly inactive. The brain has an essential offline training mode.
Absolutely, offline training. Experience replay during sleep. This is one of the most remarkable parallels to modern deep learning. During non-REM and REM sleep cycles, the hippocampus actively replays the high-frequency firing patterns that are associated with the day's important experiences.
And it replays them much faster, right?
Often sped up by 10 or 20 times, yes. This consolidation process transfers these volatile temporary memory traces into stable long-term storage in the neocortex.
How many different ML concepts are at play here at the same time?
There are several crucial ones. First, it is textbook experience replay, which is a core technique in deep RL. By shuffling and rerunning recent events, often out of order, the brain breaks the temporal correlation of experiences. This leads to better, more robust generalization.
What else?
Second, it acts as regularization. This is essential for preventing the classic ML challenge of catastrophic forgetting, where learning something new just wipes out old memories. The replay strengthens both new and existing traces.
And
Third, the process is fundamentally model compression. The brain is distilling the raw metadata of daily experience into efficient, sparse, long-term representations. The weights might be off, but the system is in a continuous high-speed optimization mode.
This brings us to the great advantage human intelligence still holds over even the most advanced AI generalization. We can learn a concept from just a few examples. A single negative experience teaches a child not to touch a hot stove for life.
While an AI often needs thousands or millions of data points.
Exactly. So why are we so much better at it?
The biological solution seems to be rooted in metabolic efficiency, which, paradoxically, leads to cognitive flexibility. We rely on sparse representations. For any given concept or memory or input, only a very small percentage of neurons actually activate. The information is encoded in the specific pattern of who fires, but the overall activity is sparse.
Less is truly more.
In the brain, yes.
What are the primary computational and biological advantages of having such low activity?
Our sources point to 4 key advantages, and they're all interconnected. First, it powerfully prevents overfitting. If too many neurons activate for a single concept, the representation becomes too brittle and specific to that one training example. Sparsity forces abstraction.
Okay, that makes sense.
Second, it drastically reduces energy consumption, which is vital for staying within that 20-watt constraint. Third, it enhances interpretability and signal clarity. The crucial signals stand out from the background noise.
And the fourth, which sounds most important.
And perhaps most importantly, it significantly enhances robustness and fault tolerance. If you lose a few neurons here and there, the concept remains securely encoded because the representation is distributed but minimal. This biological strategy directly inspired ML techniques like dropout and sparse coding layers.
This efficiency brings us to the almost mythical concept of the grandmother cell.
Yes, the term is provocative, but the underlying science points toward the reality of monosemantic units. These aren't necessarily single dedicated cells for your grandmother, but highly specialized neurons or small ensembles that respond exclusively to highly abstract, invariant categories.
Okay, let's stop there and clarify the nuance. Is it really a single neuron for Jennifer Aniston, which is the famous example, or is that just a provocative headline for a very sparse, high-level ensemble code?
It's almost always an ensemble, but an incredibly sparse and specialized one. The research, which is often done using intracranial electrodes in patients, shows these units fire reliably regardless of the context. Meaning, the subject could see a picture of Jennifer Aniston, hear her voice, or just read her name printed on a page, and this same small group of neurons would fire. The unit abstracts the core concept of Jennifer Aniston, invariant across any sensory modality.
So what's their function in our overall intelligence? Why have them?
They form stable, context-independent representations. They act as anchors for high-level concepts, which is essential for rapid generalized recognition and retrieval. Computationally, you can think of them as functioning similarly to specialized attention heads in transformer models, which are dedicated to finding specific, specialized types of relationships within the data while ignoring all the noise. They provide the stable dictionary of high-level concepts the brain builds over a lifetime.
We talked about sleep replay, but the brain seems to be in this constant battle against that persistent ML problem of catastrophic forgetting where learning something new just erases old knowledge. How do we manage continual learning so well?
The biological brain employs really sophisticated strategies that go beyond simple sleep replay. The brain rehearses experiences not just during deep sleep, but in these rapid, subtle microbursts all throughout the day.
So it's constantly refreshing its memory.
Constantly. Furthermore, it utilizes intrinsic mechanisms, particularly specific patterns of neural oscillations, that act as a kind of meta-learning system.
How do those oscillations help stabilize old knowledge while you're trying to integrate new information?
Well, they coordinate neural activity across different regions. For example, theta and gamma oscillations coordinate activity between the hippocampus, which handles new memories, and the neocortex, which holds old memories. This allows the system to encode sequential information and adapt rapidly without erasing prior knowledge. The system learns how to learn efficiently, maintaining this vast, stable knowledge base while continuously integrating new information in a way that current general AI models still really struggle to replicate successfully.
That flexibility and that ability to generalize so rapidly, it points to a system that isn't running some rigid, deterministic, predictable program. It sounds almost inherently nonlinear.
It is. This hints strongly at the idea of computational irreducibility. The brain's dynamical processes are so flexible, involving billions of simultaneous interacting feedback loops, that its precise behavior can sometimes resemble what's called irreducible computation.
Meaning?
Meaning you cannot predict the result or the future state of this system any faster than just running the system itself. There is no simple equation, no shortcut to the computation.
And this incredible architecture wasn't designed top-down by some engineer in a lab.
No, and we must always remember that. The entire structure, from the energy-saving sparse codes to the highly refined RPE system, was sculpted by millions of years of evolution's training. This vast, continuous training process, driven by survival and efficiency, resulted in architectures that generalize across countless domains without explicit programming. That level of efficiency and generalized learning remains the holy grail for current AI. The ML map explains the mechanisms, but evolution explains the optimization path.
Okay. We've established the brain as this magnificent, energy-efficient ML network. It handles logic, it handles prediction flawlessly. But that only explains how we compute. It doesn't satisfactorily explain phenomena like the unified self or sudden intuitive leaps or qualia, the actual what it feels like to see the color red.
Exactly.
For that, we have to turn to our second map, the highly speculative but conceptually rich quantum map.
And it's essential to approach this section with a lot of critical caution. The quantum metaphor is fraught with controversy, and for very good reasons. Skeptics immediately point out the overwhelming challenge. The brain is warm, 37 degrees Celsius, it's wet, and it's incredibly noisy.
All things that are poison to quantum effects.
They're the absolute destroyers of fragile quantum states. They cause immediate quantum decoherence.
So let's put that challenge into perspective. In a warm, wet biological system like a brain, what is the typical decoherence time for a quantum state? How long could one possibly last?
In that kind of environment, quantum states are expected to decohere in femtoseconds,
Which is?
1/4,000,000th of a second. Now, contrast that with the speed of neural communication, which operates on the millisecond scale. That's thousands of times slower.
So the quantum effect would be gone long before the neuron even had a chance to fire.
Exactly. The sheer scale of that challenge means any quantum effect would need to be sustained and protected for far, far longer than physics currently seems to allow in non-supercooled environments.
That is the mountain this theory has to climb.
Mm.
But if we suspend that skepticism for a moment and we look at the brain through this very strange lens, what are the concepts we're borrowing from quantum computing?
We borrow the fundamental concepts. We encode information not as classical bits, which are 0 or 1, but as qubits, which can exist in multiple states at the same time, a state called superposition,
Both 0 and 1 at once.
and everything in between. We also borrow entanglement, where two or more qubits are linked instantaneously, their fates intertwined, regardless of the distance between them. This framework views the brain as this vast, dynamic system where information is encoded across multiple simultaneous possibilities and then processed holistically, which is what enables a unified consciousness.
So if quantum processes do exist in the brain, where do Penrose and Hameroff, the main proponents of the most famous theory, suggest this is actually happening?
They look deep inside the cell with their orchestrated objective reduction, or theory. They argue that the substrates for quantum computation aren't the classical networks of neurons we've been talking about.
It's not the neurons themselves.
No, it's the protein structures inside the neurons. The microtubules. These are these tiny cylindrical filaments that provide structural support within the axon and the dendrites.
Okay, so microtubules as quantum registers. Walk us through the theoretical chain of events that supposedly leads from a quantum collapse to a discrete moment of consciousness.
According to ORCH-R, within the wall of the microtubule, you have these protein units called tubulin dimers. They propose that certain electrons or protons within these dimers can exist in a superposed state, acting like biological qubits.
So the qubits are inside the proteins.
That's the idea. The orchestrated part means that these individual quantum states become synchronized and entangled across vast networks of microtubules all throughout the brain. Consciousness, in this view, is a series of discrete events. It emerges when these superposed, entangled states collapse through a physical process they call objective reduction, OR.
And that collapse is supposedly triggered by instability in space-time geometry itself, gravity.
That is Penrose's controversial contribution, yes.
So OR is the moment the wave function collapses. It forces the system out of that probabilistic superposition and into a single defined physical state.
Exactly. And each one of those collapses constitutes a single, discrete moment of consciousness. It's the moment we define as now. The microtubule is thus framed as quantum channel, analogous to a register in a quantum processor, enabling this rapid, complex, holistic integration needed for awareness before the next OR moment occurs.
Okay, if microtubules are the quantum hardware, what components are acting as the logic gates that would manipulate this superposed information?
Well, in this theoretical model, the classical structures we already know, the synapses, would have to behave like quantum gates, like a Hadamard gate or a NOT gate, manipulating the superposed information that's encoded in the microtubule.
So the classical structures control the quantum states.
Yes, and consequently, neural assemblies would operate as multi-qubit circuits, where the complex patterns of spike firing we observe are really just the readout of these complex quantum algorithms unfolding across entangled structures. The whole focus shifts from just looking at electrical signal intensity to something called informational geometry, the correlations, the phase relationships, the patterns across vast regions of the brain.
This concept of non-local information processing coordination without direct signaling. That's what makes the quantum map so appealing for explaining the unity of consciousness, right? The binding problem.
It addresses the binding problem directly. The brain displays this astonishing long-range synchrony, which we can measure as widespread gamma or theta oscillations, linking physically distant neural populations. Quantum analogy suggests that entanglement-like correlations are what link these populations.
So it's not a signal, it's a correlation.
It's a non-local integration of memory, sensation, and emotion into a single, unified conscious moment. It's the difference between hearing 1,000 individual instruments playing their own notes, that's the classical view, and hearing the integrated harmonic symphony that they create together, that's the quantum view.
Are there any observations, even speculative ones, that suggest nature might be using quantum principles in a biological system?
The sources touch upon some highly speculative research. People are looking at phenomena that occur at the necessary scale. For instance, there are some observations suggesting potential nuclear spin entanglement in water molecules within the brain, or even the incredibly efficient transfer of energy via photon or proton tunneling along certain protein paths.
So these are just hints.
They are far from confirmation, but they highlight that if the brain is achieving this robust, holistic unity, it might be relying on deeper dynamical principles than simple classical electrical signals can account for.
And if the system is constantly being battered by biological noise, heat, molecules just bumping into each other, how would this fragile quantum coherence possibly be maintained?
That's where the brain's inherent ability to rewire itself, plasticity, takes on this powerful conceptual new role. Analogically, this continuous adaptation and reorganization could resemble fault-tolerant quantum error correction.
Like in a real quantum computer.
Exactly. In quantum computing, you need these complex error correction protocols to maintain coherence. The theory suggests the entangled biological networks are constantly reorganizing and adapting to maintain stability and coherence despite the inevitable noise and decay of their warm, wet environment.
Let's move from the theoretical architecture to the actual mental processes. If the mind is quantum-like, how does it handle something like a high-stakes decision or a creative act?
The strength of this model is really its ability to explain how we manage simultaneous possibilities. When we are planning or imagining or deliberating complex choices, the brain seems to hold multiple possibilities in mind at the same time. In the quantum analogy, thought exists in these overlaid probability fields. It's a kind of conceptual superposition.
So instead of thinking about plan A, then thinking about plan B, then thinking about plan C, linearly, the brain is in a state of A and B and C all at once until a decision is forced.
Yeah, that's the idea. Decisions don't emerge from linearly checking options one by one. They emerge from the interference patterns that are created by these competing possibilities overlapping in this quantum-like field.
And creative insights, those sudden aha moments.
Those are seen as resembling a process called quantum annealing.
How does annealing relate to creativity?
Well, annealing is a process used in quantum computers to find the lowest energy solution, the optimal solution, across an entire possibility space simultaneously. Similarly, the quantum brain model proposes that the mind searches an entire conceptual energy landscape at once and then suddenly collapses onto an elegant, previously unforeseen solution after exploring many implicit alternatives in parallel.
That would explain the speed of it.
It explains the speed and the non-algorithmic nature of human creativity far better than a slow, linear search model ever could.
And the connection to consciousness itself, that hinges on this coherent state being maintained.
The Orchor theory suggests that consciousness fundamentally depends on maintaining these large-scale, integrated, entangled states across vast microtubular networks. Anesthesia, in this view, is simply the process of breaking these states down, causing that unified consciousness to decohere and fade away.
So strong entanglement equals awareness.
Metaphorically, yes. Strong entanglement equals rewarded states or stable, coherent presence. It links coherence directly to awareness and subjective experience.
This objective reduction process, the collapse that generates the now, how does that function as a computational necessity? Why have it at all?
Penrose posits that gravity triggers the collapse. Computationally, this process acts like a highly effective biological loss function or a pruning mechanism. It achieves three things. First, it selects stable outcomes from all the superposed possibilities.
It picks one.
Second, it generates those discrete experiential moments, the temporal grain of our consciousness. And third, it acts as a filter, effectively pruning the improbable or unviable brain states, forcing reality to crystallize into a single, cohesive experience.
That provides a physical explanation for why our subjective experience, our qualia, is so unique and so difficult to share or duplicate.
And that's where the quantum no-cloning theorem becomes this powerful, evocative metaphor. The theorem states that quantum information cannot be copied perfectly or duplicated.
You can't just copy and paste a qubit.
You cannot. And we use this to illuminate why subjective experience is inherently singular. It's why no two people can have the exact same perception of a sunrise. It's why our memories are necessarily reconstructive, not perfect duplicative copies. And it's why the conscious experience, the qualia, is inherently non-transferable. It emphasizes the deeply personal and singular nature of the mind, something a classical AI with a perfect memory could never replicate. Hashtag 2.3 generalization and the warm quantum mystery.
We established earlier that human generalization is fast and flexible. If the brain is quantum-like, how would that accelerate our learning and search capabilities?
It would accelerate cognitive search through quantum parallelism. Just as a quantum computer can evaluate many potential inputs simultaneously, the brain might explore multiple conceptual paths at once, using non-local associations to produce these rapid, creative leaps. It's analogous to how Grover's algorithm can dramatically accelerate the search function in quantum computing.
That capability for rapid parallel exploration, it sounds like it would thrive on ambiguity, which is the exact opposite of classical logic.
It absolutely thrives on ambiguity. Unlike classical systems that demand huge data sets or rigid, unambiguous rules, the quantum brain model excels at uncertainty. It forms probabilistic models and maintains these flexible representations even when it has incomplete or contradictory data.
So uncertainty is a feature, not a bug.
Uncertainty is a biological feature, not a bug. Decisions emerge from those interference patterns among competing hypotheses, which allows for superior adaptability and flexible reasoning compared to deterministic classical computation.
But we cannot ignore the elephant in the room, the warm coherence paradox. Quantum computing needs to be near absolute zero. The human brain is a hot, wet biological environment. So how could quantum coherence possibly survive long enough to generate even a single conscious moment?
That is the central, legitimate scientific criticism that gives this theory its speculative status. There's no getting around it. If the or theory is true, it means that nature has engineered something that our best physicists have not. Robust, warm, fault-tolerant coherence. It implies a fundamental breakthrough in understanding how living systems can protect and harness quantum states.
So what are the specific biological shielding mechanisms that are proposed by the sources to explain how these biological qubits could possibly be stabilized?
The theory suggests a kind of multi-layered protection, specifically around the microtubules. One key hypothesis involves the structural role of structured water layers.
Structured water.
Yes. Water molecules that are near proteins don't just slosh around randomly. They form these highly organized, almost quasi-crystalline layers. These structured layers might act as a protective sheath, shielding the internal quantum states within the tubulin dimers from the thermal noise of the surrounding bulk water.
So a kind of thermal blanket built by water itself? What other defenses are proposed?
Secondly, there's the proposed role of the actin gel phases within the cytoplasm. This is the dense, viscous material surrounding the microtubules. It could insulate the structures from physical vibrations and molecular collisions that would cause instant decoherence. You can think of it as a specialized biological dampening foam.
Oh, a foam blanket. What else?
Finally, there's the concept of topological features acting as biological qubit stabilizers.
Topological features. That sounds like extremely advanced physics.
It is. In physics, topological qubits are a theoretical type of qubit designed to be immune to local noise by encoding information globally across the entire structure. The theory here suggests that the geometric complexity of the microtubule structure itself, its lattice and its symmetry, might inherently provide this kind of topological protection. It could act as a biological qubit stabilizer that prevents quick decoherence despite the warm environment.
So this moves the argument from, is it even possible, to how did nature engineer it to be possible?
Precisely. And it also gives us a new, deep perspective on the brain's Ferri's 20-watt efficiency. If the brain is leveraging quantum processes, it might be employing quantum-inspired precision sensing or using extremely efficient signals like photon or proton tunneling for rapid, low-energy signaling. While, and we have to say this again, strong skeptics maintain that classical electrochemistry is sufficient to explain everything, the quantum analogies stimulate these new hypotheses about the molecular basis of mind that challenge our classical understanding of complexity and efficiency.
So we have these two profound yet seemingly contradictory maps. We have the ML map, which explains the robust algorithmic how of learning and prediction, and we have the QC map, which explains the unified experiential what it feels like of consciousness and creativity. It feels like it's time to stop viewing this as a competition and start synthesizing.
Absolutely. The greatest insight from our sources, I think, is that the brain is not a singular type of computer. It probably requires both robust classical processing for sustained complex computation and these probabilistic, holistic dynamics for generating consciousness and creative insights. The mind has to be a multi-physics phenomenon. Hashtag 3.1, comparing strengths and limitations.
Okay, let's summarize the strengths of the ML map first. What does this classical framework successfully describe and predict?
The ML map excels at explaining what we called algorithmic intelligence. So pattern recognition, the entire hierarchical process of abstraction, motor control, robust feature extraction, and how memories are stored and stabilized through processes like synaptic plasticity and sleep replay. It provides us a superb computational language for sustained logical thought, for prediction, and for modeling the external world efficiently.
But where does the standard ML framework inevitably hit a wall when you're analyzing the brain?
It cannot fully explain the unity of subjective experience. It can't explain how 86 billion isolated neurons generate a single unified self. That's the binding problem. It also struggles to model non-algorithmic creativity, those sudden intuitive leaps, or the ineffable first-person quality of consciousness, the qualia.
So it explains the mechanics of what the brain does, but not the phenomenology of being a brain.
That's a perfect way to put it.
Okay, now switching to the quantum map.
Yeah.
Despite all the heavy skepticism and the decoherence problem, what unique cognitive features does this conceptual framework illuminate successfully?
Well, the QC analogies illuminate phenomenological intelligence. Things like the capacity for massive parallel thought through superposition, the experience of instantaneous global coherence via entanglement, the process of sudden realizations via collapse, and the brain's superior handling of ambiguity and uncertainty. It provides the only known mathematical structure that can conceptually account for subjective unity without requiring infinite signaling speed.
And its major limitation remains the lack of empirical evidence and that warm, wet physics challenge.
Precisely. Lacking strong, conclusive evidence and really struggling to overcome the warm coherence paradox, the QC map can't yet describe higher-level cognition-like complex language generation or detailed logical reasoning in practical quantum computational terms. It describes the moments of insight and awareness, but much less so the sustained computation.
The synthesis is inevitable then. One model describes the logic engine, the other describes the consciousness engine, and they must be operating in tandem.
Exactly. We have to embrace complementarity. The ML map provides the architecture for learning, sustained reasoning, and generalization across known domains. The quantum map provides the conceptual structure for creativity, intuition, and achieving subjective awareness and unity. They aren't competing truths. They are complementary perspectives on a system whose complexity just exceeds any single descriptor we have.
This leads us directly to the core idea of this whole deep dive, the multiscale model premise. We need to challenge the assumption that the brain follows a single computational principle, whether that's classical or quantum.
That assumption just limits our understanding. We have to argue that the brain is a layered system. It employs multiple computational physics, electrical, chemical, dynamic, and potentially quantum to achieve its staggering complexity. Its computational style is entirely dependent on the scale at which you are observing it.
Okay, let's break down the three distinct computational scales that are identified in our sources.
All right, at the top you have the macroscopic scale. This includes vast neural networks, cortical regions, the communication between the lobes of the brain. This scale behaves demonstrably like the ML architectures we've discussed. It's classical computation governing high-level perception, memory consolidation, and decision-making over seconds and minutes.
This is the domain of the RNNs and CNNs.
Exactly. Then at the very bottom, where the physics gets strange and the scale's extremely small, we have the microscopic scale.
This is the quantum realm.
This involves the proteins, the tubulin dimers, ions, molecular structures. It's the potential domain of the quantum-like properties described by Orr. This scale operates on the fast nanotemporal level, and it's hypothesized to support unity, creativity, and the fundamental binding of conscious experience.
And the third layer, which sounds like the most important, but maybe the most overlooked, bridge between these two giants.
That is the mesoscopic scale. This intermediate level exists between the firing of a single neuron, which is micro, and the activity of a large cortical map, which is macro. It is characterized by high levels of stochastic, probabilistic, and dynamical computation. This mesoscopic bridge is the crucial zone where the magic happens. It coordinates the low-level quantum-like dynamics with the high-level classical networks. We really need to spend significant time here because this is the scale that is most missing from our current AI models.
Now we delve into the mesoscopic bridge. Why is this middle scale, this chaotic probabilistic layer, so critical to understanding human intelligence, and why is it the key to building better, more general AI?
The mesoscopic scale is really the heart of adaptability. It is characterized by immense dynamic change where coordination and chaos coexist as features, not bugs. It's where the brain manages timing, flexibility, and ambiguity.
Let's start with coordination. The brain is constantly in flux, and that flux is dictated by these internal rhythms. So discuss the essential function of neural oscillations.
These rhythms, like theta waves, gamma waves, beta waves, they are far more than just side effects of neurons firing. They are essential for coordination and communication across vast distances in the brain. These oscillations literally link distant brain parts by coordinating the timing of their activity.
How does timing equal communication? That's not immediately obvious.
Imagine two distant regions need to integrate data, let's say auditory and visual information about a snapping twig. If they synchronize their firing within a specific time window, particularly within the rapid gamma rhythm, which is about 40 to 100 hertz, the brain treats that information as belonging to a single unified percept.
So it's a timing code.
It's a timing code. The oscillations regulate timing, attention, memory encoding, and integration. They are the conductor of the brain's orchestra. Current AI models largely lack this intrinsic temporal rhythm. Their computation is often static or purely sequential. The brain uses rhythm to organize time and synchronize vast amounts of data flow efficiently.
So if the brain wants to access a memory, it literally cues the hippocampal region to enter a specific theta rhythm to synchronize with the cortex.
That's exactly right. Theta rhythms, which are around 4 to 8 hertz, are strongly associated with navigation and memory recall. They act like a low-frequency clock signal that organizes the higher-frequency gamma bursts that are encoding the content of the memory itself. This coordination allows for this precise, temporary, functional linking of different modules, a dynamic connection that just dissolves when the task is done.
We usually talk about the neuron as the fundamental unit of computation, but the sources emphasize that the neuron itself is far from a simple on-off switch.
Oh, that is a critical realization. Each neuron is a computational powerhouse unto itself. Each complex dendritic tree, that's the branch structure that receives input, is performing local, nonlinear processing. This is dendritic computation.
So we're looking at miniature, localized neural networks that are operating within a single neuron.
That's it.
What capability does that local processing add that a simple single point of input wouldn't offer?
It adds incredible richness and sophisticated local pattern detection. Dendrites can integrate incoming signals nonlinearly. They can decide whether an input pattern is meaningful before the signal even reaches the soma, which is where the main action potential is generated. This allows the overall network to handle far more complexity and localized integration than a simplified model of point neurons would ever suggest. Our large language models, with their simplified uniform nodes, they simply lack this internal distributed richness.
And this mesoscopic layer is where the brain embraces features that engineers typically try their best to eliminate: noise and chaos.
In biology, noise is often highly functional. You can consider a phenomenon called stochastic resonance. This is where a certain optimal level of noise actually improves the detection and learning of weak signals in a system.
Wait, that seems completely counterintuitive. How does adding static improve the signal?
The noise slightly nudges the system closer to its firing threshold. So when a very weak signal arrives, the combination of that signal plus the optimal level of noise is just enough to push the neuron over the threshold, causing it to fire and allowing the system to detect the signal.
Without the noise, the weak signal would have just been ignored.
It would have been completely missed. This principle is so effective that it has been borrowed by ML. Techniques like dropout and certain types of regularization are intentionally introducing controlled noise during training to improve generalization.
And what role does chaotic dynamics play in our intelligence?
Neural populations often exhibit nonlinear, unpredictable, or chaotic behavior, particularly during tasks that require rapid exploration or adaptation. And this is absolutely not a failure of the system. A certain degree of controlled, non-deterministic instability is a feature.
Why is instability necessary for intelligence?
Because chaotic dynamics enhance flexibility and exploration. If a system is perfectly stable and deterministic, it can get stuck in a local optimization minimum. It finds a pretty good solution and just stays there.
It's in a rut.
Exactly. By maintaining a slightly chaotic state, the neural population can rapidly switch between mental states, it can jump out of those rutted thinking patterns, and it can explore new solutions in the vast conceptual landscape. It's a foundational element of adaptability and the ability to pivot rapidly in response to an unexpected external environment.
Okay, so given all this layered multi-physics complexity, the spiking, the RPE, the oscillations, the necessary chaos, it's much easier to see why modern AI, despite its vast computational power, still struggles to emulate true human general intelligence.
Yeah.
What are the essential gaps that our current LLMs exhibit?
Current LLMs are absolute masters of the classical macroscopic prediction layer. They can predict the next token in a sequence, they can generate incredibly convincing text, and they can perform vast pattern matching. But they still lack self-awareness, unified subjective experience, moral intuition, and, crucially, that robust, rapid generalization from minimal data, the child in the stove problem.
They are powerful, but they lack presence.
That's the perfect word for it.
It seems like current AI has only copied the top, most classical layer of this multi-scale system, and maybe only a part of that.
That's the critical assessment from our sources, yes. Current AI successfully copies the brain's ML architecture transformers, mimic the cortex, RL mimics the basal ganglia, but it fundamentally misses the full physics that's required for intelligence. It lacks the multiscale feedback loops, the crucial temporal coordination of oscillations, the necessary biological noise, the stochasticity, and the potential quantum mechanisms that give rise to presence and integrated insight.
It has the data engine, but it's missing the rhythm section and the unpredictable genius of the orchestra.
Precisely. It is incredibly powerful, but fundamentally incomplete. To reach general intelligence, the ability to adapt robustly to novel environments and exhibit true insight AI must move beyond simply imitating the classical macroscopic layer and begin incorporating the physics of the mesoscopic and the quantum-inspired scales.
So if we, based on these sources, were to design the next generation of AI that mimics the brain's full spectrum of computational styles, what would that integrated architecture even look like?
The future of AI, according to this view, requires integrating all three scales for true general intelligence. We have to transition from these monolithic architectures to a hybrid architecture that's composed of components mirroring the biological scales, allowing for different types of computation to handle different challenges.
Starting with the foundation we already understand and have pretty much mastered.
1. The classical ML layer. This is the logic and prediction engine. It handles language, vast pattern recognition, complex reasoning, and memory indexing. It would utilize highly efficient sparse models like transformers, predictive coding architectures, and specialized MANs for long-term knowledge retrieval. This is the layer that ensures the AI's outputs are coherent and logically consistent based on all the data it's learned.
Okay, next, the implementation of that crucial, often chaotic middle layer.
2. The mesoscopic layer. This is the bridge. It supports adaptation, coordination, and intuition-like transitions. This means implementing hardware-level synchronization using oscillatory timing like artificial gamma rhythms to coordinate communication across different component modules. It would strategically utilize chaotic attractors and controlled stochastic resonance to manage noise, maintain flexible internal states, and enable the system to break free from local optima when it's solving problems.
So this layer adds the rhythm, the responsiveness, and the adaptability.
That's right. And finally, you have to integrate the principles of parallel search and unity that we derived from the quantum map.
Okay, the top layer.
3. The quantum-inspired layer. Now, this doesn't necessarily mean we need to build full-on quantum computers to run our AI, but we must implement the principles of coherence, parallelism, and wave function dynamics. This layer would enable global integrative states for complex problem solving. It would support hypothesis superposition, where the system can hold competing solutions simultaneously and facilitate these rapid, collapse-like decision processes that mimic sudden human insights and creative jumps. This layer provides the engine for unity and non-algorithmic creativity.
The result of integrating all of that would be monumental. It would be an AI that not only predicts well, but also thinks with a kind of unified intent and adaptive flexibility.
Such an architecture wouldn't just generate text or predict the next token based on learned patterns. It would think in a multi-scale fashion. It would form insights through parallel exploration, and it would model reality as a unified whole. It moves beyond mere pattern prediction into the realm of full-spectrum intelligence, capable of making those rapid, creative, and robustly generalized leaps that are so characteristic of human minds. #OutUTRO.
Okay, let's unpack this incredible comprehensive journey. We started by mapping the brain as this highly efficient, deep neural network, powered by spikes and reward prediction errors. Then we navigated the strange and controversial realm of quantum superposition inside the cell. And we finally landed on this idea that the brain is actually a multi-physics orchestra.
Yeah, with classical, stochastic, and quantum-like computational styles all operating synchronously at different scales.
What's so fascinating here is that the search to understand the brain isn't just an exercise in neuroscience. It's actually revolutionizing how we think about all computation. The mind is this spectacular combination of the classical, the stochastic, and the quantum-like.
And each layer is solving its own unique optimization problem. From minimizing prediction error using interneurons, to maintaining dynamic flexibility via chaos, to maybe achieving objective reduction into a unified conscious moment.
For you, the listener, this means accepting that the most complex object in the known universe requires multiple, complementary maps for true comprehension. To understand intelligence fully, you need the algorithmic map of ML for the how we learn and predict, and you need the conceptual phenomenological map of QC for the why we feel and generate insight.
It requires a synthesis of both mechanism and subjective experience.
We've established that the brain is a multiverse of machines, where classical logic provides the stable framework, and quantum-like dynamics provide the creative potential, and consciousness is the music they create together. This raises an important question for future research, and for you to mull over as you explore the boundaries of AI.
If the mind requires classical dynamics for robust logic, and it requires quantum-like chaotic dynamics for flexible creativity and adaptation, what inherent limitations exist in any AI model that completely eliminates the element of controlled, necessary biological noise and instability? Can you truly achieve general intelligence without embracing a little bit of computational chaos?